So I'm a junior professor at UCLA, University of California, Los Angeles. Uh, Los Angeles is a really amazing place in the United States. It's probably got some of the best weather in the world, right on the coast of California, just a few miles from the ocean. Los Angeles is also very unique as being one of the big tech hubs, especially for engineering and medicine. And so today I'm going to present kind of a variety of results, both on a little bit on robotics and kind of physics, as well as some medical applications. Broadly, the research that my group works on is computational imaging. So this is kind of a new field which jointly designs the camera hardware and the algorithms that go on the back end. Traditionally, these topics are studied separately. Traditionally, one designs the algorithms in isolation and the camera hardware in isolation. But by bringing them together, we can potentially spawn new types of imaging systems. This is an example of an imaging system that we looked at in our lab. We have a person, and they're being captured with a camera. Not shown on the slide is that this gentleman is actually being hooked up to a machine, a health monitor, and a health monitor is actually tracking his signal here. Now, maybe it's possible, especially during the COVID-19 pandemic, rather than hooking up the patient to a bulky and expensive machine, what if it was possible to measure similar sensing schemes, but through ordinary video? So on the bottom, we have a video from a Samsung S10 phone. And what you see is we're capturing a video of the person's face, and we're actually enhancing the color signature to obtain a waveform. And this waveform is actually corresponding to the heartbeat. And what you can see is that the heartbeat almost exactly is a match to the expensive vital sign machine that the person is hooked up to. This type of research is done in collaboration with medical doctors at UCLA. That collaboration with medical doctors enables us to really scale our algorithm, not just through simulations, but through real-world patients. So here we have a patient that's, again, sitting, and he's connected to the health monitor. And we're actually able to use an algorithm that starts to chop up the face into different pieces like a pizza, blanks out the eyes and the lips because they cause spurious readings. And then we are able to actually obtain a signal-to-noise ratio map and then actually infer the heart rate from there. So we can essentially use both the spatial and temporal processing because this is a video. So we might use kind of very specific spatial cues on relation to the person's race, gender, as well as skin type. And then we can use temporal cues like the Fourier transform to end up estimating the heart rate. This person's heart rate in particular was around 59 beats per minute. Here's kind of how a setup looks in our lab. We have a person that's kind of sitting in front of a camera. Now there's many cameras and lights, so we can test a variety of situations, but really all that's needed is the cell phone camera here. And based on this lab projects, we're hoping to one day deploy this in the clinic so we can start to measure vital signs with telemedicine. And I think I've mentioned this twice already, but it's worth mentioning 3 times, is that at UCLA, there's a very, very strong integration between the clinical doctors and the engineering students and faculty. So just as one measure, our co-authors on this paper were Dr. Jalalian and Dr. Kannison. And one of the ways that this collaboration got started is Dr. Jalalian and I are neighbors. We actually have the same in the junior faculty at UCLA, they've put the engineering and medicine faculty in the same kind of residential block. So that's kind of one kickstart to this kind of collaboration. And then through Lale, then we start to work also with Maxime, who's the chair of UCLA Health and Anesthesiology. It should also be mentioned that one of the most fulfilling things about working at UCLA is the ability to collaborate with clinicians on solving impactful problems, meaning that Lale and Maxime are actually treating COVID-19 patients during their kind of day shifts. And in that process of treating COVID-19 patients, they come up with amazing insights on what the pain points on the technology solutions are. And so I think if people like us being engineers want to really collaborate, contribute to medicine, I think we really need to listen and learn from the doctors who are on the front lines making those decisions that save lives. So one project was on engineering and health. The other major thrust for our group is about physics. And of course, physics is based on health, right? The imaging physics and the light is kind of how we extracted that signal of heart rate. But I think physics goes, go ahead. But I think physics goes pretty far beyond that. One of our goals at Visual Machines Group is to kind of teach machines how to discover the laws of physics. So on the left, we have a painting of Isaac Newton. And Isaac Newton kind of sees this apple falling in the 1600s, and from that is able to kind of understand that there might be something like gravity, and later on understand, okay, how do we represent mathematically gravity? What is its significance? On the right, we have a robot that's also sitting under an apple tree, and maybe this robot, he, she, or it kind of sees this apple falling down and scribbles down that equation, gm1m2 over r squared. So the motivation here is perhaps one day in the future, if we advance AI and machine learning, we can also start to teach machines how to discover the laws of physics. So here's an example project from our group where we have one of our undergraduate students, Sid Somasundaram. And what he's doing is he's taking a bunch of basketball shots, and I don't know if they're really going in. It looks like they're missing a little bit short, but he's taking a bunch of basketball shots, and that's giving a nice arc to the parabola. Now, just from the video alone, the question is it possible to discover the kinematic equations that we know from our high school, right? X equals V naught T, Y equals V naught T minus half GT squared. Is it possible to go and discover or rediscover these equations just from the video? Now, let me emphasize why this is a hard problem. The equations that you discover, you don't know the form of the equation. It's not about discovering the variables. It's not about taking the measurements and then solving for the velocity, right? That is easier, but we don't know what velocity is. The machine doesn't know that. The machine doesn't know what G is, the gravitational constant. So the machine doesn't have this frame of reference to form these equations. And moreover, the equations themselves in their kind of form, whether it's quadratic, cubic, or something else, it's not known what that form is. Could be a sinusoid, could be a logarithm, right? It could be a combination of many different things. So how does the machine, solve that uncertainty behind discovering what's called a governing equation, which in this case is the parabola that governs the laws of physics of the ball's motion, as well as its parameters? Because it's like asking a question, if you don't know the parameters and the equation, and you're trying to solve for both, it's kind of like either you could say a chicken and egg problem, or you could say more mathematically, it's like if I tell you A times B equals C, and I give you C, it's like asking you to figure out what is A and B. So concretely, let's say I tell you that 12 is the product of two numbers, A and B. And then I ask you, what are A and B? What would be your answer?
Three and four?
3 and 4, yeah. But could be 6 and 2, right?
Yeah.
Could be 6 and 2, 12 and 1, 24 and 1/2, infinite number of possibilities. So similarly, we could plug in very different parameters than velocity and gravity and come up with a different form of equation that would fit the data. And so that's why this problem is very difficult. Here's another example. It's not just about parabolas, but here we have a motor. The motor is spinning around in a circle, and we're going to take a video of this. We take a video sequence and feed it through the AI physics discovery engine. And what that does is it outputs a discovered physical law, A cosine omega t, A sine omega t, and those sinusoids actually describe the positional motion of that ball. Here's how the discovery engine kind of works. Right? How does the kind of magic happen? Well, you take a video, and the video is not labeled in any way except for the fact that I give you the times that the video is taken, the frames, the timestamp of the frame. Based on that, we detect an object which has dynamics, so some sort of position. And then with these positions, we end up essentially putting it through a latent physics module. And so this latent physics module is able to kind of discover the key latent parameters or latent variables of an embedding space that are somehow informative. So if I have a high dimensional space of, let's say, positions coming in, what is a low dimensional representation of those? So here you can see this as L1, L2, L3. So these low dimensional positions are ideally predictive of something about the physics of the problem. And so these low dimensional positions can then be placed into essentially a genetic algorithm. And a genetic algorithm is able to go and rearrange those latent parameters to actually come up with candidate equations. So the two-step process are, first you take your input, and rather than discovering the equation right away, you discover hidden parameters, much like a hidden Markov model or similar. You discover the hidden parameters in your data, and from those hidden parameters, you then combine them in different ways to create a governing equation. And so if you look at this input video, we have students here tossing various balls. And if you look at the input video, they give you various embedding trends in the data. Those embedding trends can later be plugged into the genetic algorithm, as I mentioned, to go and form these output equations. The embedding trends effectively are variables like velocity or gravitational constant, but we don't know that in advance. We have to kind of discover that these are velocities and gravitational constants. Going forward, if we can actually go and start to discover laws of physics, it's not just about these elementary examples like rotating balls or parabolas, but maybe more complex physics where we don't have a full grasp over it as humans. Even as humans, we don't understand all the complexities of how light scatters or of how tissue, biological tissue starts to modulate light at the nanoscale. So these sort of levels of new physical understandings can arrive to us potentially by discovering the laws of physics. The work for discovering laws of physics was done by Pradyumna Chari, Chinmay, and Telgaonkar, and Yudha Ba. Pradyumna, I think, will potentially give a talk here, so that'll be terrific. Pradyumna was also the lead author, along with Krish Kabra and others, on the heart rate estimation paper. So he's been quite productive at UCLA. So this is a picture of our research group. If you're interested in joining us or meeting us once things reopen in LA, feel free to drop a note if you find yourself in California. Otherwise, I'm happy to take questions, and thanks a lot for your time.
Hello, sir, and it's been a very wonderful session with you. And from the first time I heard you 2 years ago at IISc, I've been hooked to your research, and it was a privilege of the greatest kind to host you in our organization. And as a part of IEEE NITK and SPS Chapter, I offer my sincere thanks for obliging to our request.
Of course, the privilege is mine. Thank you so much. And I think Pradyumna will be coming to give a talk here on his research. That'll be exciting to see as well. Thank you so much.
The discussions that we have had with him, and it's been really great, so very insightful.
Terrific. All right, all the best. Take care. Good luck with your hackathon.